talk started. It is my pleasure to welcome our next speaker, Martin Jaggi. Martin, do you want to start sharing your screen?
Sure.
So Martin has been also one of the leading figures in communication efficient distributed optimization and federated learning. His group has produced several really impactful results in the last few years. So Martin is an assistant professor at EPFL. He heads the machine learning and optimization lab over there. Before that, he was a postdoc at ETH Zurich, also at Simons Institute, Berkeley, and École Polytechnique in Paris. He earned his PhD from ETH Zurich as well. And he is the co-founder of the Zurich Machine Learning and Data Science Meetup and EPFL's Applied Machine Learning Days as well. So it's a pleasure to welcome Martin. Martin, please take it away.
Well, thanks so much for hosting me. It's a great pleasure. I hope it works with the sharing.
Yes, we are able to see your slides.
All right. Yeah, I'd like to continue the discussion on communication compression a bit, which is an important aspect for distributed optimization, distributed machine learning. So for the start, I want to keep it open a bit. So we will have different kinds of distributed learning, right? So the basic setting is very simple, that we have a data set, which you can see maybe on the top right. But that data set has been distributed among all these devices. So that we don't have the whole data set on each device, but everyone only has a part. So in that setting, we want to learn, we want to train a model which is as good as the model on the centralized data. And how we can do that is we need communication. We need to talk to each other among the devices, which can be either by a server or maybe in a more direct way in a peer-to-peer system, for example. Then we will go to decentralized learning. But I want to talk a bit about both, and I want to mostly talk about the communication aspect on how to get these updates across efficiently. And so one motivation for this is that the systems, of course, are getting more complex, the hardware. So there is communication happening in all kinds of places between the devices, between parts of the device, between chips and all kinds of sorts, or between mobile phones and so on. So how we're going to approach this is very standard. Of course, we will use the workhorse algorithm in the whole machine learning field, which is gradient descent, more specifically stochastic gradient descent, which you all familiar with. So here, just the notation is we have I, our data point, and the model is W here. So we perform on our device, we take one of our own data points, we compute gradient of just one data point or one mini batch, which you have on the bottom here. So that's what we would do if you do training alone. Then we would update it just the standard way. We add a bit of the negative gradient to our old model here, and that's our new model. Now, if you're in a collaborative setting or a distributed setting, then the server also gets involved. So we want to maybe share these updates we perform with the other workers, so that we can also benefit from their work and share our progress and compute the average of all these model changes. So delta W will be the model change. So now models are big. So models have terabytes in size in some settings. Can we, instead of sending this full size gradient, which is exactly as big as the whole model, can we send something cheaper? So that's the question, of course. And you can ask these 4 models, or you can ask these 4 gradients. So here I'll focus mostly on the gradients, which are the objects that we want to send for a second. And this will actually change in the second part of the talk. Then we will more talk about sharing models between nodes. But for now, it's gradients. And how can we make them smaller? We can quantize them. We can compress them in other ways. So for example, instead of a 16-bit or 32-bit floating point, you can just send 1 bit. That would be one approach. Another approach would be to ignore the smaller magnitude entries altogether and only send the entries of biggest magnitude. That's the approach which was proposed a few years ago by NVIDIA, which is called deep gradient compression, which was kind of the first empirical paper showing that it's actually possible to still do deep learning when you or even less than 1% of the entries can sometimes be enough to be shared among the workers. What we want to do here is another compression going to low rank of our gradient. So what does that mean? Actually, if you think about it, the gradient of a neural network is a matrix, basically, because the layer here, if you look at one layer, is also a matrix. So every change you have proposed for each edge is an entry of your gradient. So your gradient is a matrix shaped. And therefore you could ask, okay, can I take that gradient and also approximate it by a low rank variant of that matrix? Say that is the basic idea. So far, so good. And if you visualize this a bit more, you can see that on the left you say have the original gradient as it comes from backpropagation, and then on the right you can see all the different compressions you could have. For example, just 1 bit per entry, or you have most of them set to 0, like in the top K case, or you only send a random subset of the entries either uniformly spread around or maybe in a block, which is also a possibility, but turns out to perform a bit worse usually. Or here is kind of our approach to use a low rank matrix. I hope you can see my cursor actually, maybe. So okay, that's the visual picture. And how does this work? So you can compare the different variants of compression. Either the 1 bit approach is like the sine approach. You can either just send this sine or the other ones we discussed. And then you compare this to the first row here, which we have no compression at all. Then every epoch you would send the full gradient, which gives this amount of communication. And then, of course, if you compress, here you would send like 32 times less. You can ask, do I obtain a similar test accuracy? Yes, more or less, it's slightly lower than before. And also that might cost you some time. Hopefully it's more efficient than when you send the full gradient originally. And the same works for low rank. And for low rank, you can have a much more significant reduction in the size, because especially for layers which are in a shape like a fully connected layer, which has both the input and output layer size is very big. Therefore, the matrix is big and kind of square shaped. Therefore, you can have, when you only send this one vector, or rank 1 approximation will have a size which is like vastly smaller than the, let's say, n square, which would be the original gradient. So, any question on this?
Hi, Martin. I have a quick question.
Sure.
So yeah, I guess this is like the power SGD paper. So I had the question like when I read the paper as well. How do you actually, like, when you take a SVD or a low rank decomposition, how do you make sure like the interpolative decomposition kind of like holds? As in, like, how do you make sure that weight WI corresponds to WI? Like, you see what I mean? Like in top K, when you are, or like some sparsification, if the coordinates of your compressed G corresponds to the coordinates of your original G. But in PCA or SVD, whatever, like, that is not the case, right?
Yeah. Okay. I guess I get what you mean, that there should be a correspondence that hopefully they directly correspond, which in this picture, yeah, it seems a bit broken, right? That's also the intuition you have, right? Here you see, if you have the low rank on the right, it looks very, very different from what you originally had, right? So is that what you mean by the correspondence being a bit broken between the different entries? And that's a very valid comment. And yeah, it sounds a bit too easy to be true. And this is not to the end of the story. So I actually want to discuss a bit more about this, and I think we'll get back to this a bit more. So yeah, this is not the end of the story. So because there's a lot of issues, and here are three very big issues. So you mentioned SVD, right? So one thing is SVD is out of the question. It's way too slow, right? So that's one concern we have, which we want to discuss a bit, because backpropagation is surprisingly fast, right? We all think about it, it's quite a complex algorithm and so on, but it is actually very efficient computationally, right? It's linear time in the number of weights you have, right? You throw a constant batch size to your network, you do this forward pass, it only costs you linear time in the number of weights in each layer, and same for the backprop pass. So, so that's linear time, which we do not have at all if we look at SVD. So SVD is of course not linear time in the matrix size. So if you go back and look a bit at this time, so yes, there is actually something to say here. So the compression time is really essential. So this is talking about milliseconds here, but when the backpropagation only takes like 200 milliseconds, then it's not okay to actually do an expensive compression operation, such as anything which is more than linear time. And even if you look at top K, even that would require sorting of your entities, basically. So here, if you actually look at these numbers on the right, then you see that even sorting is actually out of the question. It's not competitive enough because even sorting is too slow. Okay, you can be smarter, you can have a heap data structure, so on, but we have to be very, very careful with the efficiency because backprop is so fast. So that's going towards this first point I want to discuss a bit more, which is the speed of decompression and compression. And how to do this is that actually, yes, we are going to use power iterations instead of using the full SVD of that matrix. So how does that work? You're probably all familiar with the power iteration. How it works is just you take one random vector, which you here call Q. You multiply that by your gradient, which is the matrix here, and that's the result. The nice thing is it's matrix vector, right? It's really cheap. So this is linear time, so this is cheap, cheaper than backprop. And same, the thing is doing it once is actually not enough because this is a rectangular matrix. So we need to do it again with the transpose of our matrix. And then we have our approximation, which we call calligraphic C. C of our gradient that's a compressed version of our gradient. And what it actually is here is this rank 1 matrix, which you can get by P times Q. Okay, I should have said that P would be normalized in every step. So you can do this with rank 1. You can also do this if you want to have a higher rank, then you, instead of just using one vector, you will use several vectors. So Q will not only be one column vector, but it will contain several columns. And then you have to add an orthogonalization step after each iteration here. That would be a variant. But let's just think of rank 1 for now. The whole argument is kind of the same. Another thing we need to think about, because is even doing power iterations, it might still be a bit inefficient because it would take, as we know from linear algebra, it takes a long time to converge really closely to the true rank 1 vector, which we probably should. But then you said even the true rank 1 vector you're not so convinced if that even is a good idea compared to the original gradient. So yeah, it seems that we lose a lot in this approximation, which is true. So therefore we have to be careful to do this approximation well in the little time we have. So what we will also do is the second trick is to actually use the P's and Q's we got from the last iteration from the previous batch, well, many of the batches we have seen in our training so far. And so we will just use the previous P and Q and then take those as the initialized right-hand side to multiply with our fresh gradient on a fresh batch. Maybe some of you are familiar with OJAS algorithm. That's an old algorithm to compute the PCA or the top eigenvector singular vector. If you don't have the full matrix available, but if you only have stochastic estimates of the matrix available, which you want to approximate. So you have a kind of unbiased estimators of this matrix around, can you use those to approximate the first principal component or the first singular vector? So, and the answer is yes, you can. And that's exactly by doing a power iteration of the stochastic estimate every time. It really is really the same as stochastic gradient descent for learning, where every time you get a different batch. So you also have unbiased stochastic estimate of the function you actually care about, which is all data points, but you only see one data point at a time. But Oja's algorithm tells us that if these points are matrices, then yes, even then it's okay to keep multiplying your P's and Q with this stochastic matrix, which you see a fresh one every step. So if the gradient, if the weights would be fixed, then this true gradient of all data points would be constant, right? Then we would have exactly Oja's algorithm. So, and then we would know how that converges to the best rank 1 approximation of this full gradient. However, we are doing neural network training, so the gradients are actually changing, the weights are changing. So that's why this is not a theorem. This is only an intuition, so to say, because the gradient here is changing in every step. So, but we can have like reasonable, relatively weak assumptions that saying that the gradient is maybe not changing very quickly when we change our weights, right? So here I'm not talking about the stochastic gradients. I'm talking about the full gradient over the whole data set. If that one changes slowly, then we could say that this is very close to Oja's algorithm, where we converge to the best rank 1 approximation of this. So this one we have actually not formalized as a convergence theorem. If anyone is interested to prove this, that would be a nice thing to do as well. So, but yeah, we know it's true for constant gradient. Okay, and what this says is, of course, if using this this vector from previous steps, is a much better idea than just throwing it away every time using random initialized P and Q in every step. So we see actually a big difference of that. Okay, I hope this makes a bit of sense. And then the second challenge we kind of have to address when we do this is, actually, I was very imprecise on like who talks to whom, right? So I was saying that, yeah, there is a node and there is a cloud, right? But the information really has to go from everyone to everyone. And that's in this first part of the talk, we talk about the data center, also the all reduced setting when everyone actually can talk to everyone, but we still have to be very efficient that everyone gets the result. So the result is the average of everyone's update. So this, the communication pattern we would like to have is that everyone shares their update with everyone, which naively takes n square communication, which of course is extremely inefficient if you have n nodes. So that's a big problem. Another problem we have is that to actually use the more efficient schemes, which we have like on the right, which is a tree-based reduce pattern, a communication pattern that like just two nodes talk to their parent, and then the parent averages these two, and then they again average to the next level. So you only need logarithmically many communications happening here, which is much more efficient. The problem is this only works if your communication compression, the C operator, is actually linear, right? Or that it's associative, so that you can actually do this in different orders. So, and that is a big issue, right? This is not satisfied for many of the communication compressions we know. For example, think about the top K, or even if I select a random K entries among my gradient, that's my communication compression. As soon as I merge them here, the sparsity is not K anymore, but 2K. So they become more and more dense as long as the more you aggregate towards the server. So most compression methods which exist do not satisfy this linearity. Therefore, we cannot use the very efficient communication patterns which enable fast all-to-all communication, which is called all reduce in the high performance computing literature. So it would be really nice if you would have this linearity here, because then we could do that. And then if we have this linearity, Another promising hope we have is that it will also be better to deal with non-ID data, right? Because if every node has a different distribution of data, the sum of all nodes would still have the correct distribution, right? But the individual ones are biased. So we have to be very careful not to lose the ability to deal with non-ID data. So, and I think the talk after this one will go much more in depth on actually proving how to deal with non-ID heterogeneous data. So we want to support all reduce. The nice thing is that, okay, I talked so much about the problem, but the solution is actually very simple because the power iteration is linear. So that's why this problem here actually has disappeared. Yes, we can use all reduce because it's very simple here. You see, if you have two nodes and they agree with which Q to start, they apply their individual gradient. So each node has their own gradient, but they multiply with the same Q, then the compression of the sum of the two nodes is the sum of the two compressions. So it's just because the vector matrix is linear. So that's all. This problem is solved. We can use all reduce, which is nice because then you can save a lot of communication. All right. There's still another issue to talk about because even if we have all these nice properties and fast speed, we still have to be a bit worried that our gradients, when they're now compressed, they are not correct estimators of the original gradient anymore. And what do you mean by correct? I mean that they would be unbiased. So maybe they might be stochastic or so on. So I would say that in expectation, I would hope that at least in expectation, my compression should be the true gradient. Is that the case? So it's quite easy to see that this is not the case for example, top K, if you do the entry-wise. It's also not the case for the rank 1, which is what we are doing. It's also not the case for, here we have an example of sign SGD. If I just take the plus minus 1 as the sign of each coordinate of my message. So what you can see here is the dotted lines, S1 and S2, these are the sign, these are the compressed versions of the original gradient. So the solid lines, G1 is the true gradient I had before. And the dotted line is my compressed version. It looks fine, they're almost aligned, so nothing bad so far. However, if you look at what really happens is that here in this example, you just have 2 data points. How do you see it? That you will make 0 progress to go to the optimum if you just alternate between steps here. So you sample step data point 1, data point 2. You will always only move on these compressed vectors. So you are really stuck. So this is really a counterexample that this algorithm here, which is called sign SGD, cannot work. What this shows is that SGD, when applying the compressed gradient, will fail in general, especially in these cases where the gradient compression is not necessarily unbiased. So because you always stay on this diagonal line, which is dashed, you will never make progress towards the red, which you should. So how to fix that? That's also a very easy fix, which was actually also known for many years already in the literature. It's called error feedback. So I mean, even if maybe I can say the simple scheme is just whenever you have like numerical operations and the errors are going to add up if you do many iterations, right? So that's the problem. But in those settings where you actually know how to accumulate this error, you can actually accumulate it and then feed it in again in every step you do, so that it kind of resets. And whenever you do an error again, at least you have added the previous error. So that's the intuition. Let's see how it really works in the case where we are interested, which is gradient descent. So on the right, you have the true gradient, which you would like to move towards. On the left, you have the compressed version of it, which is a bit wrong. So what you do is you just continue. You would go next. I would again use my true gradient, but I cannot. So I would actually So I actually moved to my compressed direction. But the key trick here is that the error which I did in the step before, so I know how much I was wrong in the first step. That's the red arrow. So I don't forget this. So in the second step, when I have the next chance to compress something, I will say that, okay, I wanted to go to this true gradient, but also I know I had this error. So I will add the error back in before I do the compression again. So I don't compress the thing here, which is the traditional approach, but I compress my desired step plus the error I've accumulated in the previous steps. And that's where I go. If you do this, you can show that you can do arbitrary compression qualities and you will converge. So here there is no condition that the compression operator needs to be unbiased or anything. The only condition you need is that the compression operator has this simple property here. So basically, just that it's bounded in Euclidean norm, and the quality you measure this is called delta, which we measure here relatively to the true thing that you want to compress. So this is the notion of compression. Yeah, sure.
I had a question about the error. So this error needs to be stored on the device, right? So that takes can increase the memory used by a factor of 2.
Absolutely, yeah, that's right.
Are there any works on compressing the error? I know it's like we are compressed.
You're completely right. Thanks you. Yes, we need memory for this. So every worker needs to have this additional buffer which stores their error accumulated so far. And yeah, that's a problem. But yeah, I haven't seen any work actually which can still do the error feedback while getting rid of this size of the buffer. But I think some recent works are studying this. It's a very good question. That's great. And yeah, it's a factor of 2. It's maybe not the end of the world if you say that, okay, Adam compared to SGD is also a factor of 2. But yes, it is an issue if the models are really large. Thanks for that.
Yeah, Martin, this is Arya here. So I think so Tirtha asked, like, can you also compress this error? Like instead of just keeping the error, if you just compress it into few bits, is that
a compressed version of the error? I think there was a paper trying this recently. It's a good idea. But you also have to make sure that this error then does not accumulate. The error on the error does not accumulate. So maybe it's worth trying. Yeah, good idea. So,
okay. Yeah, thanks.
Because the proof strategy here kind of works that we control the error absolutely, which is the same strategy as you know from the virtual iterate analysis in SGD, which people also use to analyze, for example, asynchronous SGD. So,
yes. Martin, I have one more related question.
Sure.
So, suppose you have a federated learning scenario where only a subset of these nodes participate in every round of training, then how would the error feedback mechanism work over there? So let's say a node stores the error, but then they are not selected to participate in several rounds. Is there a way to fix it? That would be quite interesting. Because the error will become stale after a few rounds.
You're right. In like federated learning, you're right. We will need that, but I'm not sure. I haven't thought this through, but I think it should work because the thing is, both will become stale. Like both the actual gradient, you also missed that one, and then which is not a problem of staleness, but a problem of missing it, but that is easy to analyze. But then you're right that the error becomes stale, and that is less easy to analyze. I think it can be done, and also great question to look into. I don't know it by heart. So.
Thanks. Yeah, it would be quite interesting to look at this as well.
Yeah, absolutely. Thanks a lot for comments. Yeah, so this is just this is not about power SGD. This is about compressions in general, and this is just to show that usually when you have n workers here, then the number of workers n only goes into, the number of workers n is helping you, right? So you really benefit from having n times more worker, you are n times faster. So that's the first term, but the second term is actually slowed down with the compression. But the nice thing is that the first term is completely unaffected by the compression ratio. If you use error feedback, if you don't, it will not even converge. So, I mean, there might be other algorithms, but SGD with naive compression will not converge. There are other comments, otherwise.
I have a quick question, Martin. So for the power SGD work that you shared, so how do you get delta?
Yeah, great question. So I will get to this in a second. Actually, it's quite easy to get the delta if you use a random projection. So which means if you just take one step, you just multiply your gradient with a random, let's say, random vector p from a sphere, then it's quite easy to see how much magnitude you get in expectation from this random projection. So then it's understood. However, if you have this kind of warm start phenomenon that you don't have a uniformly random p, but one which you got from previous steps, or from previous power steps, or from previous SGD steps, then we're not so sure. That's also something that could be studied further. So we only know the delta precisely for a random Q. And we know that the one from power is better empirically, but we're not sure how to prove that the delta you get from many power steps is probably better than the one from, I mean, in the SGD setting. If you do power on a static matrix, then I think it's easy to show. Yeah. Cool. Yeah, I think that summarizes a bit the whole discussion on power SGD. So I mentioned these three big issues, which are overcome mainly because the whole thing is actually a linear operator, which is really convenient for many things, that it's suitable to all reduce, so you can just plug it in. And what I should also have said before is when I showed you the experimental result, what's kind of nice is that there were absolutely no hyperparameters which have been tuned. So, okay, to be honest, the algorithm does have one hyperparameter, which is the rank, and also maybe how many power steps you want to do. But apart from that, we did no changes at all. So we just used the same learning rates as people have already used without compression. So there was no changes necessary. So it's kind of convenient in practice. And yeah, this has been also integrated into PyTorch by the developers of PyTorch. We don't know them, but they implemented this, which is very nice to see in the version of 1.8, which came out. And we also learned that DALI, this recent system, which combines text and images, was also using this compression, especially if you have GPUs, it's quite essential to make the communication practically faster. Apparently on TPUs, it's less of an issue, but on standard commodity hardware, this can be a very convenient trick. And if you don't have hyperparameters tuned, it's makes life simpler, because this is especially useful for training big models, right? And when training once is already so expensive, you don't want to tune even more hyperparameters to also get the communication reduction working. So that's the summary of the first part, I would say. Any other comments? Good. If not, I would like to move to so here's the link. Also, I'll state it again. In the end, so now I'd like to move a bit to the second part, which is on decentralized. So what if we really want to do decentralized learning? So decentralized meaning without server coordinating. So the motivation here is to really allow some, it's like in federated learning, right? You would like to allow new applications where people don't want to get the data out of their device. And it would also be greatly advantageous to not have the trust in the server which is needed, so that just the users themselves could decide to team up and start a collaborative training. That is the goal. And we think that would be nice, because then all the choices on privacy and to participate or not could be very aligned with the user who actually owns the data. So that, I think, would be very promising if it's possible, but also where it's quite challenging, comes with a few additional challenges compared to when you have the server, right? So this is what we already discussed. Of course, it's a very successful approach to enable new applications. But again, as I mentioned, the issues can be a bit that control over the data is not with the origin anymore. So I don't want to say anything bad about particular companies, but just this is how all the decentralized learning applications currently work. So we want to go a bit further and bring back a bit more of the control to the devices which is already done a little bit by federated learning, because in federated learning, at least the data remains exactly where it originated on, and only gradients are communicated, which is already an improvement. But still, then the utility of the resulting model and the whole control aspect is still with the central coordinator. So can we go this one step further to really do the same thing, just without a central coordinator? And that's what decentralized training is. And yeah, the situation is completely the same as initially. It's just that here, we don't want that one server needs to coordinate everything, but we want the devices to directly reach out to each other and exchange messages and arrange, train together, reach a consensus on the model or an approximate consensus. So that's the goal here. And again, what do we send here? So we can send gradients, or for those of you who are familiar with, this has been very well studied in the literature for also a few decades to study how to reach approximate consensus in such a setting. So if you forget about learning for a second, if you just think that every node has a value, can we compute the average value over all nodes in such a decentralized setting? And that is usually done by gossiping, which just means we pick a random edge here. The nodes will average their two models or the two values. So then those are now closer together. And then next step, another edge between two nodes is activated, and they can reach consensus on a vector, say, which here in the machine learning setting will be the model vector. So that's the goal. There's many challenges here. It's really, I think it's significantly harder than the standard federated setting, because privacy is a bit harder to achieve. Also, the robustness is also harder to achieve, because then if you have malicious nodes, it's in a federated setting, it's kind of easier to kind of detect them, and the server let them decide on, okay, these get kicked out. But in a decentralized setting, it's harder, like who you can trust or not. So that's an interesting aspect. The incentivization is going to be tricky. I don't have any good answers there yet, but I find it very fascinating to study all these four aspects. And today, I just want to talk a bit about the efficiency, which is just what we had before already. So how to compress our gradients basically in this decentralized learning setting for more communication efficiency. Okay, so what we're going to do is to just try to throw the same idea as before also to the decentralized setting. And as I said, the basic methods that people use are gossip based. So you just think that your this node here has model 1, then here is another node that's model 2, M2. What they want to do is they want to average their model. So then now both their models get replaced by the average of the two. So that would be what you have on the last line here if there's no compression. So of course, computing this average of two models is tricky because they are so big. So if this is a terabyte, you really cannot afford sending the whole thing. So you want a fast update, especially these are like, if you think about mobile phones here talking to each other, then it's even more important to be efficient because you actually have to pay for your data plan for every bit you send. So can we do this with communication compression? And doing this, I mean the averaging of the two models without ever sending something the size of a model. So what we want to do is to apply our communication compression to the message we want to send, which is the message is kind of the average of the two models. So can we do that? Let's take the same compression as we had. So we try to build a rank 1 approximation of that sum of the two models. So that you have on the right. And again, we will just start with a randomly initialized vector Q, applied to some of both models. But okay, now that's what we would like to do, but we cannot do this first line. Why? Because neither of the nodes has both models, so it doesn't work. However, you do very advanced mathematics to go from the first equation to the second equation, and you see that you can actually compute the same thing if you just exchange a vector with each other without ever exchanging a matrix with each other. So I'm, let's say on this node 1, so we need to agree on the same Q. That's a small catch before we do this scheme. So we have the same random generator, so we have the same Q. I will compute my model times Q, and you will compute your model 2 times Q. Now the result of that is a vector. We exchange those, and that's our compressed version of the model, which is P. Okay, to be honest, that's half of the compressed version, but then we will do it again to do the same thing for Q. So again, the key takeaway is we will never want to send a whole matrix, which is a gigantic size. We only want to send vectors, and this is the vectors we send. I send M1Q to you, and you send M2Q to me. And that's it. And then we can both compute this compressed version. So that's the whole trick, basically. You do it again to get the Q. And if you want, you can also do this for higher ranks if you have a whole collection of Qs which are orthogonal to each other. That's the scheme. Let's see if this also works. And to analyze this, we need a bit stronger conditions on the compressors that we had before. So if you remember from what we discussed before, we said that any compressor is fine which satisfies the box on the bottom. That just Euclidean norm must be relatively small compared to the original thing. That seemed fine, but now I have a bit of stronger condition. Now I want to enforce that my compressor is actually linear. This will be, remember we said that this linearity was nice for all reduce, but there it was more for practical purposes, or well, yeah, for the thing to actually be sound. But here in decentralized it's even more interesting that this property that they need to be linear, that's going to be a key property to make the proof work. So otherwise we cannot make this proof if we do not have linearity of the compressor, as in the first line. Another slightly technical condition is that if you would apply the compressor again, then it should stay unchanged. And another one, which is slightly more strong than we had before, is that the delta is now measured this way. So maybe your compressor is stochastic, then you need that in expectation, it's maybe not the true W, but it needs to be at least a good fraction of the true W. So that in particular, the direction of this thing must be correct. And the magnitude, you cannot have a magnitude of 1 here, which would be the perfect compression. But even if you have less, it's okay. So you can have arbitrary bad quality of compression as long as these two additional conditions are satisfied. If we have such a compressor, and again, it is very easy to show that a random rank 1 compression, which means I use a random P vector or Q, and multiply them with my matrix, it's very easy to see that this property is satisfied. So it's harder to see if we then do many iterations and do it on a changing gradient, but if you just do it as a random projection, it's very easy to see. So if we have this notion of a compressor, then the convergence rate is nice. So we can have conversions of SGD in the decentralized network. What does that even mean? So the convergence is not about every node converging, but the convergence is about the average model of all nodes converging, in the sense to go to a flat point, or if you're lucky, it's a local minima. If you're unlucky, it's a saddle point. So that's what we show. Gradient of the average model being small after 1 over epsilon squared many steps, which is standard. And again, so the first term looks pretty much like it should be. And then the second and third terms here, those are actually then affected by the compression, which is called, which is captured in the delta fraction, the compression quality. Then the row here is the topology of the graph, which also comes here if your graph is more connected and is converges faster. So the row is standard for what we know for decentralized SGD without compression. So, and now what's maybe, and another boring thing is the sigma square. Sigma square is just a very standard variance of your gradients on a node. It's just an amount of noise you have on a node. So here is the stochastic gradient, and here is the full gradient on that node. So they are the standard sigma squared. So that's completely the same thing as centralized SGD, same thing as decentralized SGD without compression, everything same. The only thing which is actually quite interesting is the zeta here. So now that zeta measures heterogeneity of the data. So the data between, it can be heterogeneous between the nodes, but it should not be too crazy. So that's what we measure with the zeta, that what you have on node I varies from the average of everyone's data only by zeta square. And that's, so you have, so when you have a higher zeta, that means your data is more heterogeneous. So then you will get a slowdown in the second term. So, and yeah, I should have maybe said the L is standard smoothness. Okay, that is the convergence result for any such compressor. And then also in practice, this works quite nicely. We practically tried this on some standard graphs and data sets. So here is a language modeling task, which is a standard LSTM on Wikitext. This is with 16 nodes, and it compared to other algorithms which are available to do compressed decentralized, which is mainly the Choco algorithm, which actually allows arbitrary compressors, which are even a bit more general than the ones we have here. But the Choco algorithm has more hyperparameters which need to be tuned. So there's two kinds of step sizes, one of the consensus and one for the optimization. So it's a bit more tricky to get it tuned, but we did compare to a tuned thing. And the good thing about this compression we have here is that there's no hyperparameters. So it is nothing of step sizes, so it needs to be tuned. So we just took the standard step sizes actually from centralized learning even, and those then worked fine. You got almost the same loss than with a well-tuned one. And the communication compression you see on the right is also quite nice. And the graph here is a difficult graph. This is a ring, which makes the information kind of slowest to diffuse through the ring. So that's always one of the important test cases. If you look at image application, you look similar. Here is a bit smaller with only 8 nodes, again on a ring, trying on CFAR 10. And you also see it's not better in accuracy than anything, but it gets almost the same accuracy as the very well-tuned competitors, which have up to 3 hyperparameters. And here then you have basically no hyperparameters you need to tune. That's the second part. So in summary, we basically have power iterations both in the centralized case, which is coordinator, and on arbitrary graphs in a peer-to-peer fashion. And the code is available as well. And with that, I'm happy to take some more questions.
Thanks, Martin, for a wonderful talk. Are there any questions? Okay. I had a question about the second part of the talk. Do you assume any sparsity on the connectivity graph of the devices?
By sparsity, you mean like a minimum edge degree, a minimum node degree or something?
Yeah, or maximum node degree. Like if all devices can talk to all other devices, it might be very computationally difficult to implement.
Yes, you're right. That's important in the topology. So this is on a ring, right, which is constant degree. And from what I know, it really depends a bit on your application. So from what I heard in data centers, actually that's interesting that in a data center you would also use the same kind of algorithms. There's a Facebook paper, Stochastic Gradient Push, which says that okay, we don't need all reduce in a data center. We can use a decentralized topology in the data center, and there usually they use a constant maximum degree, as you say, usually degree 3 or so. You actually there, if you can design the graph, then you would actually pick an expander graph basically to have very small degree and very fast connectivity. For us, we did not look into this, what the graph, what is the best graph or not. We only measure in this row here, which is the spectral gap of the graph topology. But any graph which is connected is fine. So,
thanks. A follow-up question on it was you mentioned some examples like mobile devices at the beginning of the second part of the talk, and I can imagine people may want to do people are moving around, so the graph structure might change as a function of time. Would do you think similar results hold even in that case?
Yeah, that's a very good point, and I think much more work is needed on this. So we have looked into changing graphs when they're changing in a moderate way, such that like the expected graph you have is still okay. That we have studied a bit, but not combined with compression. So that is still open, I think. And then I think what is really tricky is when the graph gets disconnected, or when you have like systematic failures, right? But it's not when you have failures which are not like the node uniformly fails over time every second step. But if you have systematic failure of that node is really just gone for a long time, then we have to combine it with asynchronous analysis, but again, which are not with a standard delay model. But I'm really not sure. So maybe some people have some ideas here. What would be a nice realistic delay model or model of changing graphs, which would allow us to capture realistic cases for, say, mobile phones. Yeah. Also, it's not so trivial to deal with like new nodes arriving and then nodes appearing forever. That's tricky. Yeah.
Thanks. Are there any other questions?
I have. This is Arya again. So I have a question, Martin. So the conditions that you show for the decentralized setting, the compressor that should satisfy, seems like linear sketching is going to be one such thing, right? So I'm not sure whether that would be yeah.
So, absolutely. Any linear random projection, that's like the first thing we were thinking about. Then it's very easy to show linear random projections, which means pick a random vector and throw it before or after your gradient matrix. So yes.
Right. So would something like this the 1-bit compressions that would work? For example, like you take a linear sketch and then just sending the signs.
Or you would like combine both. So yeah, maybe two answers. So this thing also works for entry-wise compression of the matrix. So you can just preserve a random subset of the entries and kill the others to 0. That's completely fine because it's also linear. Now you're saying I take a random vector project, and then now I have a vector, and then I could throw further projections at or compressions at that vector, such as a sign. I think in practice it's a good idea, but if this condition would still be maintained, maybe yes. Yeah, I have to think about it. So,
I mean, the linearity condition would be violated. I'm not sure how crucially you're using that. Because overall,
yes. Really well, this one is crucial for the proof because the proof really works that we do an average consensus, right? So that's also why you see in the result the proof is not even about the individual models, but it's about the average of all models. So it really needs this. Maybe it can be approximated there. So, but yeah, we cannot do the sign in this case here.
Okay. Yeah. Thanks.
Thanks, Martin, for a wonderful talk. Let's give a round of applause for both the speakers today, both Himanshu and Martin.
Thank you.
Thank you. Now we are going to take a short break and we are going to join the postcard session in roughly 10 to 15 minutes. We have approximately 30 posters on different topics ranging from communication efficiency, distributed optimization, distributed learning, statistics, and federated learning. The postcard session will be on gather.town website, and you would have received emails on how to join. Arya also posted the instructions in Zoom chat right now, so you can take a look there. Once you join, you will notice that there are 2 poster rooms, and each poster room has roughly 15 posters. If you have any trouble joining, feel free to ping me or other organizers in this group chat. See you all there in a bit. Thanks.